Is it working? Yes. All right, good morning. Thanks for being here. So I'm going to talk about this work today, which is really hot out of the press. This is my first talk on this work, which is great because this is a very initiated audience. Most of you work in RL, and it will be a great trial for this work. So what is it about? So full disclosure, it started with trying to do Thompson sampling with Q-learning, but then we realized there's a lot more that I don't understand about this, and so we started from something much, much before we started to do Thompson sampling. One of the things that I'm really excited about or had fun doing this is that I was always not clear what is the real difference between average reward and episodic setting. And from the questions I saw in the last talk, I think many people think of them as two different things. Often when you talk about average reward, half of the audience shuts down because they work in episodic. And if you talk about episodic, the other half shuts down. So this work hopefully will try to a little bit understand that these are kind of related, not just technically, but also in terms of the algorithm design ideas and things like that. So I would try to get this message across. So this is joint work with my student Shipra Agrawal, same last name but not related. And he's actually in India getting married right now. I couldn't be there because I had to be here, but congrats to him. So this talk is slightly different from the last talk where we saw a full information setting and like an optimization problem connected to RL. So there we saw how do we find the optimization problem of finding the optimal policy or the optimal value. Here we are thinking more of RL as a decision-making problem, thinking about how to use the feedback when we are taking decisions, think about it as a decision model that we are trying to learn while also trying to optimize the strategies. So the inception of this work was actually during my stint at Amazon, where I came across a number of RL problems which didn't fit into either episodic or average reward setting perfectly, right? And I'm sure a lot of you who have done industry work have seen this where none of the settings seem perfect for it. So here is an example of some kind of things we try to do with RL, or at least repeated RL, where we are learning from the environment. For example, we might want to so the problem where I saw this was online shopping, where a customer has a shopping session and they're trying to, and the provider is trying to optimize their shopping session. And these sessions are kind of episodic in the sense that you have multiple of these sessions going on one by one. But on the other hand, they're not fixed length episodic. You're not trying to say that, oh, there are like 10 steps left and now there are 9 steps left. And so you're not trying to find like a time-dependent policy or anything. You are thinking of this as some kind of episode which is bounded. Sure, they're not going to be more than so much time, but you don't know how long they will last. Depends on your strategy, their context, and a lot of other things, right? And this is true in many of the settings like game playing, repeated game playing, where we don't know, depends on how the customer or how the player is playing. The episode might last very long or very small, but usually there is a time, like it's much smaller than the overall length of their trial, right? So one of the things about why I felt this is not a good setting for episodic RL is in episodic RL, you typically are thinking about the time horizon. And it's not about whether the time horizon is fixed or not. The problem is then you are thinking about a time-dependent policy because the optimal policy really cares about how much time is left. And that doesn't seem like the kind of solution you're looking for in these problems. You're not thinking about, oh, I have like 4 steps left in the game. You're thinking more about, I want to win this game. And probably whether I win or lose, it's not going to last more than a certain number of steps, right? The other side of using RL is really the single thread of long-term decision-making problems where you have something like inventory problem where you're ordering stuff over time and in the long term you want to optimize something, like your revenue or some other kind of customer satisfaction in the long term. And this is typically the examples we use when we talk about single thread of experience average reward RL, where we think about over a long term, I want to maximize total reward or average reward. I'm not going to reset stuff just arbitrarily at every 10 steps or something, right? But here also, if you observe, we usually are able to do this. We are able to learn in this single thread of experience without repetition, is because we assume there is some kind of repetition in terms of the model itself. Like, we usually use the fact that either states are being revisited very often, and for example, in inventory control, often there are states like out of stock or full, inventory full, whichever strategy you use, you can expect they will be repeated, okay? So there are some frequent states like this often. So motivated by these observations, so this is an overview. I will go into these assumptions in more detail later. But the idea here is that we came up with this assumption, which is, let's consider MDPs, where the only assumption I'm going to make is that there is some frequent state that is visited in at most H steps, right? So this applies to both these settings that I gave you earlier. So for example, in a fixed length episodic setting, the terminal state or the start state is being visited every H steps, at most H steps, but there are also average reward settings where there might be such states. For example, if you're training a robot, maybe the robot needs to be charged, but whatever strategy you use, it needs to go to the charging station every so often, or it will always like stand or fall every so often, doesn't matter which strategy you use. So this is the main assumption we make. And the idea is that we'll show that this assumption captures both average reward and episodic setting. And not only just technically, because technically you can make other assumptions which capture both, but we will also show that the algorithm design ideas, we will be able to transfer it from episodic to average reward setting in a very clean way, okay? So the results, just a summary of what I will talk about. First of all, I will show you that we came up with this very intuitive, in my opinion, and you can tell me your opinion later, extension of episodic Q learning to average reward setting, in the sense that the ideas will look very natural in terms of how episodic Q learning works and how average reward Q learning will work. And it will be a very clean model-free algorithm, which is not just technically model-free, but it will actually look like Q learning, right, for average reward setting. We are able to do this by coming up with a new Bellman type operator. It's a very simple operator. So we all know, and I'll discuss this more later, that Bellman operator doesn't have doesn't have a strict contraction in average reward setting, like when discount factor is 1, which is why all these problems come in the first place, right? And we'll show that this operator will have a strict contraction under our assumption, and which is what will give our algorithm in a very natural way. And as a result, we will show that, we will show a regret bound which looks like this. Yes, it doesn't have the best dependence on H, but it comes close, and the episodic result is just a corollary of our average reward result. We don't have to prove it separately. It doesn't match the best bound available for episodic, but it's not too bad. I'll discuss these comparisons later. The last result, which I will not discuss, we can also show that our regret bound will imply a path learning bound because of the nature of our algorithm. Yeah. All right. Any questions? I want to keep it very interactive. I wrote the slides in a very classroom lecture kind of way, so I will discuss basics of Bellman equations for both settings and why this follows from the other and so on. So feel free to interrupt. Yeah. Yeah, I will discuss it. I will compare it to other assumptions that were made, how weak it is, how strong it is, compared to other assumptions made. Yeah, I will have this slide on that. Yeah. Yeah, right. So I'll skip through this quick. Yeah. Very different. So I'll show you why if, so one of the, for example, finite horizon MDP optimal policy is non-stationary. In this case, it's stationary. Then you would be suboptimal, right? And No, the other thing is that I'll discuss is one of the big issues with using finite horizon setting is that you know that the end of the horizon, the reward is 0. And that gives you the whole dynamic programming structure, and that's gone here. So that will be the biggest issue due to which you cannot just take that algorithm and apply it to average reward setting. And estimating that value function in the end of that time, or the frequent states value function, is the main challenge in the average reward setting, because that's actually the asymptotic average reward. Okay, so I'll skip through this quickly just to set the notation. I'm basically using Putterman book's notation. So that's state is S, action is A, my Bellman operator will be L. You have this kind of interactive agent playing every time they see a state, they take an action, they see a reward, they see the next state, and they keep going. Okay? The goal is to optimize some form of average reward, some form of aggregate reward. I'm not saying average reward, but mostly the talk will focus on average reward setting. Then I will show you how episodic just follows from it. Okay. So what is the average reward setting? And this is, I want to go through it a little bit because it seems a little mysterious. It's not really. So the average reward setting, we talk about a single thread of experience, which means you're from time 1 to time t, you're not artificially manually doing any resets. There might be states which are kind of reset states, but we are not doing any interruption, right? So what we want to do is we want to minimize regret, where we define regret as the difference between t times the asymptotic average reward. So the benchmark is the best asymptotic average reward that you can get. How is that defined? That is defined as you run any policy, and you look at the average reward that policy achieves, and you take that limit of that average reward as t goes to infinity. That's the average reward of that policy, and then you find the policy that has the best value of this rho pi. Okay? So that's your optimal asymptotic average reward. In fact, you might complain, why is this a good benchmark? Why am I not saying the best policy for t time steps? So we will show that under relevant condition, which is true for our condition, actually this t times rho star is within square root t of the best policies reward over time t. So at least in case of the assumption that I am making this is true. It's not always true, but for our assumptions this will be true. So you can imagine my regret as being nothing other than in time t, what's the best reward you can get versus the reward the algorithm got. Okay. This is not obvious. So if you look at the paper, we prove this, but this is only true under certain assumptions. One of them is what the assumption we are making. Okay. So I want to come quickly to the Bellman equations because these will form, this is like one of the reasons that this is how we formulate the regret, okay? Because this rho star, this asymptotic average reward is very, very important in thinking about dynamic programming for average reward setting. And we saw the dynamic programming equations for discounter setting earlier, and I want to connect it to that. So for something called weakly communicating MDPs, and it's okay if you have never heard of it, it's like a connectivity property, which says that, so the technical definition is that in your MDP, there are two sets of states, recurrent under any policy, recurrent and transient, and all the recurrent states can be reached from each other within finite time, okay? We will show that in under our assumption, this will be true for our MDP. So under this condition, this mysterious condition, yeah.
So is it like for every policy there exists this split, or there exists this split for every policy?
So there are a number of definitions. So under every stationary, so one definition is under every stationary policy, you can split the states like this. Yeah. And that will be true for us. I think there is a more relaxed definition as well, which is basically there is some policy for every 2 states. Yeah. So if you have this weakly communicating MDP, then we can write the Bellman equations in a clean way. Otherwise, also there is a version that you can write, but it's not as clean as this one. So in this property, under this property, one nice thing is that optimal policy is always stationary. And this asymptotic average reward is same starting from any state of the MDP. Okay? It doesn't matter which state you start from. Rho star doesn't depend on state. But you have another important quantity which basically will act as the value function in the discounted setting. And this will be used in the Bellman equation. So what is this quantity? And this is usually what, in my experience, in my class, students get more scared about. But it's nothing to be scared about. Think about what value function is. Value function in discounted setting is you start from any state, what's the value discounted value you will get from that state. But if you write that with the discount factor 1, that will be infinite, even with bounded rewards, right? So you don't want to do that. So what do? You kind of adjust it. You say, I will not count the total value starting from any state because that's infinity. I will count the difference between that and the asymptotic average reward. Okay? So I will not count the total reward. I will count reward minus rho star, and so on. So if I do that, then that's what we call bias, but I will just call it value, okay, just so that I can connect it to the discounted value setting. Okay? So it's like an adjusted value function, so that I don't have infinite. So if you have bounded rewards then this is bounded. Bounded rewards, bounded state space, then this is bounded, whereas value function is not. So I will call this value function, but this is what I mean. Yeah. Yes, because this is rho star is like the asymptotic average reward. This is kind of, think about when you start from a state, you have not immediately converged to rho star. Rho star is asymptotic average. But initially, you have some gap, right, on the rewards that you receive, depending on which state you start from. So different states have different value function, or what we call bias, right? But they have the same rho star. So asymptotically, because of the connectivity property of the MDP, they have all the same asymptotic average reward. But that initial gap is what we call bias, or the value. Oh, you're right. I made a mistake. Sorry, this is not there. I'm sorry. Yeah. Oh, that's a very good catch. Yeah. I think I copied that expression and I forgot. Thank you. Yeah. There's no 1 over t. This is the total value, right? Total value adjusted by average reward. Thanks. Yeah, that would have confused everybody. Yeah. So I think I said the definition that holds under our condition, but yes, in weakly communicating MDP, it just says that you should be it doesn't have to be transient under all policies. Yeah, I forgot the exact. I think the definition. Does anyone remember? The communicating definition is that for every 2 states, there exists some policy. Okay, let's just say this. Under our assumption, under every policy, you'll have these 2 sets. Okay. That's always true? No, but all the recurrent states are reachable from each other in finite time. Yeah, that's the condition. All right, so you have this Bellman so once you have defined this value function, you can write the Bellman optimality equation in the pretty much the same way as discounted setting, right? So in discounted setting, you had this gamma here, right? So and no rho star here. That's the discounted Bellman equation, right? But if you remove this gamma, mean you make it 1, you cannot possibly imagine this to be true because you are kind of, unless there is some very strict condition on this P, you cannot have it in general to be true. So what we have is that on the left, we also have this asymptotic reward, average reward appearing. Okay? So this is the Bellman equation for average reward setting. If you write it compactly, it's basically in discounted setting, the equation is V star equals LB star. L is this Bellman operator, this operator over here. And in the average reward setting, you just have this rho star appear on this side. Okay? So mainly, if you are very familiar with discounted reward discounted reward Bellman equation, then just have this extra rho star here. Okay? The 1 is the vector of all 1s because rho star doesn't depend on the state. Okay? V star is the value vector. So when Bellman operator is just defined as a regular Bellman operator without the gamma, so because the gamma is 1. Okay? So if you can solve this Bellman equation, if you can find a V star and rho star satisfying the Bellman equation, you will also be able to find the policy because it's simply this argmax. Optimal policy is the argmax policy of this right-hand side. Okay? So what we do in RL algorithm design for average reward setting, we are trying to solve these Bellman equations. Okay? Just like in discounted reward setting, or I'll discuss episodic later. But we are trying to solve these Bellman equations, and there are 2 kinds of algorithmic paradigms depending on how you solve them. Okay? Model-based and model-free. So in model-based, you're trying to first estimate this unknown reward, and because the model is not known, we are in the uncertain, not in a full information setting, so we only have to observe rewards and transitions, and we don't know this model R and P. So model-based setting will say, let's just observe all the rewards and transition, batch them at certain points, and different algorithm batch them differently, and try to get empirical estimates of these models, and then solve the Bellman equation, for example, by value iteration or any method that's efficient to solve these equations. Okay? That's model-based. Model-free tries to do this in a online fashion, in the sense that it doesn't try to explicitly build these model, but every time an instance of these reward and transitions comes in, it uses a value iteration kind of update to just update the estimate of the value function, or we will see Q value function, for example. Okay, so this is for example, Q learning is the model-free algorithm, which is one of the most popular model-free algorithm, which we'll focus on today. So there is a technical definition of what people call model-based and model-free. Like model-free is technically the one that takes SA space, whereas model-based could potentially take S squared A space. And based on that, some works kind of technically call something as model-free algorithm versus not. I don't want to go too much into that. To me, like, what's interesting about model-free is more the algorithmic concept. And our aim in this work was to keep that Q learning structure intact rather than making it technically model-free by using certain amount of space, right? So there is a gap in average, yeah. No. But you will see the exact assumption in some sense, yeah. Mixing time is more about like mixing to a stationary distribution.
But the mere fact that there's a state that we go back to every step, is that definitely not justify a mixing time bound as long as you consider the lazy block?
No, maybe, yeah, I don't know. Yeah.
Okay.
Yeah.
I think it might, but I'm not 100%.
Right. Okay. Yeah. Mixing time. Anyway, we will assume this is true for all stationary, non-stationary policies. So we don't even care if there is a mixing or not. Yeah.
I'm just saying, I think that assumption might imply a mixing.
If you go back to a state,
Every 8 steps.
its steps.
Then as long as we do the lazy lock, I'm not 100%, but I think that might be enough to imply.
By mixing time, you mean that the distribution converges to a stationary distribution. Yeah.
Like 8 steps is enough to have your instance.
Okay, maybe. Yeah.
I mentioned this because in that case you can reduce the discount again at a cost.
Yeah, maybe. Yeah, we didn't worry about discounted because yeah, I'll talk about discount later, but yeah.
I'm just wondering if those pieces together will let you apply discounted algorithms to these black boxes.
No, so basically I will show you that our assumption is actually satisfied by most works in this area. So any work that involves like hitting time or I'll show you a number of works on this model free Q learning, all of them satisfy our assumption. Yeah.
Sorry, why is that rule out reducing
But I have to talk to you about what you mean by discounted setting. Because the regret definition changes.
Yeah, I realize my
So-
is definitely a little tailored to optimization.
Yeah, because the regret is tricky to define in discounted, and yeah, so I have to talk to you offline about what you mean by
Maybe
discount.
I'll ask later, I wonder.
Yeah. So the optimization is a very different. Like main issue is that like the definition of regret can be very different in discounted setting because you need to have a long term. Yeah. 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 All right. So now let's go back to. So there is a gap between model-based and model-free in average reward setting in the sense that for model-based, we actually have near optimal regret bounds. Okay. So for model-based algorithms, we have achieved so there was initial work which had very simple algorithms, then more smarter algorithms came through. Recently, earlier the lower bound was achieved by not so efficient algorithms, but recently there has been claims to achieve it by efficient algorithms. So model-based algorithms, this problem, regret minimization problem in average reward setting is almost solved. Model-free is a little bit tricky. So let's go back to like the Q-learning algorithm, for example. So Q-learning algorithm is based on this idea of value iteration, right? So value iteration is simply you take the Bellman equation and you start with a value function and then you update by applying LV to it. And this is same in average reward setting. Even in average reward setting, when we do value iteration, the algorithm is the same. It just converges to the value vector within span, okay? Because there is a row star like a displacement to it. So the value iteration algorithm for average reward setting and discounted setting is the same. You just use gamma equals 1, keep applying V. You will not converge to a value vector, you will converge within span. Okay, so you'll have some extra constant added to all the terms. So this converges to span in some certain condition. In particular, weakly communicating is not enough. Okay, so in the Putterman's book, there is a very strong condition about like how on the transition matrix under which you kind of get an effective discount factor, and under that condition, this converges. Okay, so and Q-learning is just implementing this, and this is for average reward setting. If you want to implement Q-learning for average reward setting, you would simply take this value iteration algorithm and implement it using samples, which is basically Q-learning. Okay, so you will every time you see a reward, every time you see a state, you use your current Q value estimates and you take an argmax action, and then you simply use some kind of alpha like a learning rate and update your Q functions. Okay, and if you want to do this with a small regret, you need to use some exploration bonus there. Okay, and this is the key to having small regret. And because there is no discount factor, we need some kind of contraction property, and I'll come to that later, for which weakly communicating assumption is not enough. The existing work, the closest existing work which does this for Q-learning for average reward setting is this work by Wei et al. In 2020, which basically uses these discount factors which are adaptively, which are changing over time, like artificial discount factors, and they are able to get T raised to 2 by 3 regret. Okay? Because as you change your discount factors, you're kind of lose in terms of reward. Because when you're using a large discount factor, you're not using the optimal policy, right? So there may be that partially answers. Yeah, right? But that only gets a T raised to 2 by 3. So let me now come to our setting. And there are other model-free works which I'll display later in a table, none of which are actually Q-learning. Like there are some modification of these things, and they also have to make other assumptions. So what is our setting? Okay, so our setting is, so formally speaking, I already gave you an overview, that there is some kind of frequent state, which we call S0, for which every policy in this MDP or every policy under consideration visits in at most h time. Oh, I stated the other version of the assumption, which are actually equivalent. So actually, the assumption is not this assumption. The main assumption is that the expected time to visit this frequent state is bounded by h. Okay. Actually, this is equivalent. I will show you later, because if your expected time is bounded by h, then you visit with half probability. You visit in 2h. Okay, in at most half probability. So these two are equivalent, and this is also one version of the assumption. So under this assumption, first of all, we can show that MDP will be weakly communicating, and the span of the optimal value vector will be bounded by 2h. Okay. So any results that are for weakly communicating with bounded span, it will hold in this case. Okay. And in this case, episodic setting becomes a special case. And just as a quick recall of what episodic setting is, so in episodic setting, you are thinking of a finite horizon setting, right? So you have a h horizon setting. And the dynamic programming is not Bellman equation anymore, because you have a terminal condition, right? So this is 0. In the end, you get 0. And then you can just like do a simple dynamic programming. Like VH is defined as the optimal value from h minus h plus 1 steps. And then you can say that the last step value is 0, the previous one is L of that, the previous one is L of that, and the first state value is L raised to h of that. Okay? So that's the actual dynamic, what we in OR call dynamic programming, right? So that holds in finite horizon setting. And in that case, the regret is defined as if you had t over h repeated episodes in time t, then the regret is defined as compared to in every episode you get the optimal value from the first state, what is your total reward, okay? And this is what you're trying to optimize in episodic setting. And I have this kind of a pedagogical section in my paper where we show that, oh, if you just do this reduction, then the Bellman equations nicely connect to each other and everything. But that's just for fun. So I know most of you have seen it in some courses. But what you can show is just an overview is if you make this like terminal state as that frequent state, then everything becomes related. Like this regret is same as that regret, and so on. Okay, and most importantly, our assumption of visiting every h steps is satisfied. Okay, and now coming to the question that many of you are eager to worry about: how strong is this? Like how good or bad this assumption is? First of all, so here's a list of assumptions that a lot of papers. So there has been a lot of work on trying to do model-free algorithms for average reward setting. And I will list out the other works which don't make these assumptions, but lots of them actually make many such assumptions. And I want to just compare to those assumptions. First of all, most of these assumptions are like hitting time assumptions. And these assumptions are saying, in addition to mixing, so mixing plus hitting time, so they are essentially saying much stronger. They are saying that under every policy, every state is visited in certain length of time. So hitting time is not some state is visited. It's every state is visited in t hit time. Okay, or there is a lower bound, the probability of visiting every state. Okay, which is very different from visiting a frequent state. You could have many infrequent states in our assumption, right? So in particular, if you have any of these assumptions, you also have our assumption satisfied. And other thing is that all these constants would actually always be at least s. Because if you have every state is visited in let's say t hit time, then t hit has to be at least s. right? So on the other hand, H in our case could be a constant, like some frequent state could be visited in constant time. The other assumptions, which is like the classical book assumption, is the assumption about assuming this like discount factor. Like this is the most basic discount factor that you can get in average reward setting, which is that from any two states you go to a common state in one step. And this is considered often to be not so useful because this is directly saying putting a condition on the transition matrix, and it is saying that it is not satisfied by episodic setting, obviously. Like in episodic setting, there is no common state, you go in one step to. Yeah, was there a question? Yeah. That's the definition from that book. This is not my definition. So it says that the worst for, like if I took the maximum probability, like think about the minimum probability across all states and actions. So all the rows of the transition matrix, you want every pair of states and actions to go to a common state. Yeah, the worst probability, and you're lower bounding it. And that's what they call, so if you have this bound, then it can act as a discount factor. Then your L operator will have gamma contraction, and then all the proofs will follow. So this is if in class you just want to teach average reward setting, and you don't want to teach new techniques for convergence, then you assume this gamma, and then all the proofs or discounted factor will follow through. But this is a very strong condition because it directly puts a condition on the transition matrix. And it's not satisfied by episodic or even all these hitting time assumptions and so on. Okay. So I hope there is some satisfaction about why this assumption is not trivial and doesn't make the problem trivial. Because even after assuming much stronger hitting time assumptions, the algorithms in these papers are not trivial, or the analysis, right? Okay, so what does our assumption give us, right? So why did we make this assumption? Why is it enough? How do we get this contraction from here? So what we observe is that the contraction, we don't get L operator contraction, but we get a contraction for this operator that we call L bar. And the L bar operator is simply this average of this L operator, L squared, L cubed, and so on. Okay? And hopefully now you can see the connection to episodic setting a little bit. Okay? So if you look at this L bar operator, we can show that it has this kind of contraction, 1 minus 1 over 4h. 1 over 4 is coming because of the half probability to reach. If you have a p bound on the probability to reach, then you can get in terms of 1 minus p over h. Okay? So this is by substituting like 2, reaching half probability to reach 2h. Okay? So you get this contraction, and I'll not go through the proof, but you can imagine why this is happening, because every two policies, basically, if you look at the value function starting from any two states, in h steps they will reach a common state, which means their span will be like the 1 minus 1 over 4h, a part of their value will be the same, which means the span will reduce by that much. Okay? Yeah.
If you instead had contractivity for a different distribution over the first stage powers, would that be enough for your results to go through?
Sorry, say that again.
So it's like this. I mean, if instead of having contractivity for like the average of the first stage powers, you had contractivity for a different distribution of the first stage powers, would that be enough for the algorithms to go through?
I don't know what that means. Like, oh, so you don't want? Yeah, I think we need. Yeah, I agree.
A different context combination.
Yeah, if you have some other operator like this, which you can estimate, then yeah, it will go through.
And if I understand right, this immediately gets results for mixing time also. I guess it gets a big distribution. Mixing is enough that always is contract.
I don't think so, because like the other paper that I mentioned does assume mixing, and it doesn't seem to be.
So sorry, L is not contracted, but L to the H is contracted.
We can talk about it. Yeah. All right. I'm not completely sure, but that it will be enough, because I cannot play L raised to a, like the problem is I also need to design an algorithm which can estimate this operator. Like I need to implement this operator using Q-learning. Yeah. Okay, so I won't go through this proof. All right, so just to summarize, this is our assumption under which we have this L bar operator, which is contractive. So what is our algorithm now? So the algorithm is, look, take your value iteration algorithm and apply L bar to it, right? So if you keep doing that, because of the contractive property, you will have that, you will converge to this V star. The V star, the value function is the vector for which L bar V star minus V star has span 0. So in case of discounted, you have this relation, or you will have this relation. But in average reward setting, because you have a row star here, you only have this relation in span. Okay? Yeah.
So can I think of that span condition as instead talking about both V star and row star? Do you
No, span is just saying like that V star and LV star are not the same. There might be an additive constant in front of.
But
Yeah.
if I think of this as sort of constraining both a V star and a row star and a V star together.
This condition? This is just the Bellman equation. Basically, this equation is just saying span of V star minus L bar V star equal to 0. Span means like max minus min of a vector. Basically, you don't have LV star equals V star in average reward setting. You only have that the span of that it can be away by a constant added to all of them. So I'm just saying V star satisfies this condition for average reward setting. It also satisfies this for discounted, but it satisfies something stronger for discounted. Right? So because of this, yeah. Oh, I can. Hi, Java. So because of, if I could implement this value iteration while learning and so on, then I would get a nice convergence to V star exponentially like I get in discounted setting, right? So the main challenge is, just like I implemented Q-learning using, like evaluation using Q-learning, can I implement this using Q-learning, using just samples? And this is where we will use our idea from episodic RL. So if you think about episodic RL, we are actually estimating these L raised to H operators, right? So in episodic RL, we are trying to estimate these value functions. So there, just to remind you, the dynamic programming says this is how the optimal value functions are related to each other. VH means when H minus H plus 1 steps are remaining, and it's actually L raised to this, right? So if we use episodic RL, we could possibly, we would be estimating these functions, right? L raised to H. So we could average them and then get our L bar operator, okay? So that's the main idea. And the episodic RL has similar Q-learning as the non-episodic setting. So basically you have, instead of using one Q function, they use HQ functions, so that when you are at episode index H, you look forward to QH plus 1, and you form your target like this, and then you do your Q update, right? So in episodic RL, you have HQ functions. QH plus 1 is defining what's the value for remaining steps from H plus 1 setting, okay? So this is what we are also going to do. We are going to use HQ functions, just like episodic RL, so that we can estimate L raised to H for every H, and then we are going to average them occasionally, okay? So for this episodic RL, we do have guarantees, right? So the scene for model free in episodic RL is much better. Actually, there is like near optimal guarantees. The algorithm we will base our design in is by Chi-Jin and co-authors, where they propose this kind of learning rate, which has a clean, nice algorithm with near optimal guarantees. Okay. So we'll have two things to handle when we use this episodic RL. So in episodic RL, at step H, how do we make a decision? Because we are at episode step H, we just use the value function at H, right? So that decision is simple. We are at episode H. The value we hope to get is QH, right? Or value function at H. So if we use that value function, we are gold, okay? It's aligned. And the other thing in episodic RL going for us is that the value function at the last step is 0. So we don't have to worry about that one. These two things are not true for us, right? We are not at step H. There is no step H, right? We don't know where we are. We don't know how far as the frequent state we know will be visited in at most H, the capital H steps, but it could be visited in next step, or it could be visited in 3 steps later. So we don't know which value function to use really in that sense. In fact, value function is not different based on where we are. And we want to estimate all H, right? We don't want to estimate in a given state only a particular H, because we want to average over H for all states. So what we will do is that every step we will randomly sample little h, and we will use that value function. And that will allow us exploring all little h in all states. Okay? The other thing that we will do compared to, which is not done in episodic RL, the other thing we will add is that occasionally we will use these as value function estimates, VH, and we will average them out. And the nice thing is we don't have to batch anything to do that. We can just do a running average, okay, and update our value functions as we go. Okay, so these are basically the two changes we make compared to episodic RL. The rest of the algorithm is essentially similar. Because of this occasionally update, we have to run in epochs. In every epoch, we will update this terminal value. So this terminal value is the key. Like this is what we don't get from episodic RL, and this becomes the main difference in the analysis and everything. Because this terminal value is what is converging to asymptotic average reward in the end, okay? Or the value function in the end. So, all right. So if we do this averaging, then we are essentially implementing what we wanted to implement, which is the keep applying L bar operator and converge to V star. So here is the algorithm, and I have omitted some details. Mainly the details I have omitted are mainly about controlling the span. Like if you look at Q-learning for episodic or discounted, you control the value, right? So you say that, oh, the value cannot be too large because I know the value is bounded by h or whatever, so I can truncate it. We don't truncate it because our value can be as large as, like, very, very large. We just control the span. We just say the span cannot be very, very large. So we truncate it in span. We don't truncate it in value. And the other detail that I've omitted is the initialization. So we cannot just initialize, because we have an optimistic algorithm, we cannot initialize this to just h or something, because we don't have an upper bound of h on the value. Value can be very, very large. It can keep growing. So we initialize it a little bit more carefully to achieve optimism. But we don't do any initialization like run or anything. It's just a fixed initialization. But besides that, the steps are the same as episodic plus that averaging added in the end. So every time you see a state, you sample, you take an action based, you sample an h uniformly at random. You do argmax of q, just like in Q-learning to take, but you do argmax of q of h, or that randomly sampled h, okay, to take an action. That means that whenever you are doing this, whenever you are using a particular ht here, then I'm learning that L raised to h, right? I'm learning that q value. And then you see the reward in the next state, and then I do the update very similar to Q-learning in the episodic setting, right? So whatever h, but one difference is that I update for all h, okay? So I don't update just for the Q value, just for the h that I used to play the action, because Q value doesn't depend on action. How I chose the action doesn't matter in Q value update, right? It's offline in that sense. Once I have a state and action and a transition, I can update all these Q values for all H. Yeah.
Action you select is the optimal action with respect to a random, with respect to an operator that averages with respect.
No. I just randomly pick one of the Q. So think about it like this. I want to estimate all L raised to H, right? But I am choosing the action for one of them, which means I am essentially getting a sample for one of them. So it's more like exploration. Yeah, because I don't want to just, if I choose round robin, for example, then it might get correlated with the states that I'm seeing. So I don't want that. I want every edge to be explored in every state. So that's all it is.
I guess the exploration bonus do not mention what first. So is there any need to use the tree function you estimating to select actions? Or?
Oh, yeah. It is very, very crucial because this Q will be equal to the value function. Because the arg max, value function is max over A, right? So this will be the value function. This will be VH, but this will not be VH plus 1. Yeah, this is very crucial to select it uniformly at random, or you can use other criteria depend if you had more information. But yeah. Like in the sense that I don't want the one H to be less estimated in one state than other, right? Because I don't know how to, when I have my error bounds, then I want L bar to be estimated for all states. Yeah, so that's why we get not so good bound for episodic, right? So in episodic, if I knew that this state only comes in step H, then I should synchronize it. But if I don't know anything, then I don't want to take that risk, right? So because I could be wrong. Yeah, so if I wanted to implement this for episodic, then I shouldn't be doing that because that's why I will get an extra H dependence because of that. Yeah. It's only extra H introduces, yeah. Because I'm kind of wasting time exploring H that are not necessary in this state, yeah. All right. Where was I? Yeah. So the Q learning update is exactly the same, and this is the main new step, right, which was not there in episodic, which is why we did all this, like why we using. So our ultimate goal is to estimate this, and this is the L bar operator, right? So the L bar operator is implemented by taking average of all these VH, and this is just the running average. So if I wrote it more simply, I would just say take average of all the VH estimates in the states visited in this epoch, but I'm just doing a running average. Okay. So this is implementing the L bar operator, this part. And the epoch breaks just whenever there is more than certain, like when the number of visits of a state increases by, like it's a typical doubling kind of epoch, with this special selection of this C. Okay, so the results are some regret bound. Just want to compare them to some existing. This is the customary table that we give. So out of all these papers, the assumptions made in, so this is T raised to 2 by 3. They don't make any assumption, and they actually have the closest to real Q learning algorithm, I would say. But they get T raised to 2 by 3 because they use these artificial discount factors. These are also model free, but different techniques, not exactly Q learning. And they all make these assumptions, which we show are strictly stronger assumptions than what we make. Okay, about both mixing time and hitting times. Okay, This is a very notable paper that doesn't make any of these assumptions. It only makes weakly communicating assumption, with H star being the span bound. So this is like the weakest assumption paper, I would say. However, besides the regret bounds having a high dependence on S, I think the more important thing for me is that maybe a little controversial, but the algorithm they have is kind of model-based in the sense that it keeps track of this transition, like pairwise state information, but they carefully make sure that it's only order SA information, which is okay. Technically, it's called model-free if it takes SA space. But like for me, it was more like, can we actually do a Q-learning kind of, keep the model only kind of algorithm? So yeah. Yeah, so that's it is a very clever paper. I just feel like this was not the kind of thing we were looking for. We wanted to actually do a Q-learning algorithm, okay? In episodic, obviously, there are much better results because there, as I said, you can use the fact that H is directly connected to the state you are in, the terminal value 0, so you don't need to estimate the terminal value and so on. All right, how much time do I have? I can use some time, yeah. So I can actually go through some proof techniques. Hopefully I will be able to convince you that the proof looks complicated in the paper, but actually the ideas are not that complicated. So if you think about it, what are we doing, right? So we are implementing this value iteration algorithm through samples. Right, so the value iteration algorithm, what we are doing is this terminal value, this H+1 value, we are trying to estimate it by applying L-bar operators. And we are hoping in every epoch we apply this L-bar operator once so that we quickly converge to the optimal value function. So after K, your span, the gap between the optimal value function and your value function decreases exponentially with K, right, because of the span contraction property. So this is our aim, and we are implementing it through implementing these estimating this VH, each of which are these many L operators applied to the current terminal value. Obviously, when you apply samples, the story is not that simple because you're not really updating the full synchronized vector, right? You're only updating the state that you see, and that creates the whole issue of why this estimation problem becomes difficult. So the main key ingredient, I would say, which brings everything together, is this lemma, is the optimism lemma. And I would point to a few things here. It looks complicated, but if you think about these two components, this is just, so we are saying how close the value function is to what we want it to be, right? So what do we want it to be? It has these many L operators compared to the terminal value. And the terminal value itself is these many L-bar operators compared to the K steps previous terminal value, right? So this is a combined thing saying that if you compare to the K epoch's previous value, I have the K L-bar operators and H minus H+1 L operators for any VH right now, okay? So why do we write it like this? Why not just write these two separately and then just combine them? So that's fine for the optimism, like this is the optimism part, saying that this is at least that much. So if I had to write only the optimism part, which is this part, saying my estimation is at least L raised to something of that, then I could just have written it in separate way and then combine them. The problem is this part. The problem is if I write this, the upper bound on how this, we also have to write the upper bound on the gap. And if I write this upper bound and then I recurse on it, then if I apply L-bar to this error, then it combines the errors across states. And I don't want that because different states are explored, have different errors. And if I apply L to those errors, then they get combined in mysterious ways and I don't know how to control it. So that's why I write this lemma which says, okay, at time t, if I go back K epochs and compare my estimate to that point, then how many L bar I have and how many L I have, and what's the gap between them. And this is some recursive expression combining all the bonuses that I accumulated during that time. Okay? But importantly, it only depends on the state that I am in. Right? So it is different for the state I'm in. It doesn't combine by using an error operator, different errors in different states. Okay? So it's like a path starting from my state to the back to back. And this is complicated. I didn't give it the expression for a reason. This is like a recursive expression. We don't even define it in long form. Okay? So, and the similar optimism lemma we get for Q value. Again, Q value is also compared to the previous K operators, previous K epochs, and then the error is bounded by that. So that's my optimism lemma. But this is the part that I like the most about the analysis, because this is a very, in my opinion, a textbook kind of analysis about how the regret, I think, should be decomposed in this case. Okay? So what do we have from optimism lemma? Like I'm calling it optimism lemma, but it's really an error lemma because I have both upper and lower bounds. So I know at any state, so I'm just writing this as V, like this complicated vector. This is H minus H L operators and K L bar operators. Okay? If I look back K epochs. So I'm calling this vector as V. So what I have from, in a succinct way, I can write my optimism lemma saying that my VH value, my estimate of value function, is at least L of this V. Okay? And my Q value function is R plus PV of this V. And now this, in Q value, the action is important, right? So I cannot say, so I'm saying, look at here, I'm using the HT value I used, and I'm using the action that I used using this Q value, okay? So I'm using optimism lemma on this Q value. Why? Because this I know is same as V, right? Because AT is the argmax action of this V, because HT is the H I used when I was taking this action. So this is V. So this will let me write this will let me substitute V here, which means that the left hand side of these two equations are the same. Okay? So I can use this to write this, so I can cancel out the V from the left hand side, and I can write this equation. Okay? So what is this equation saying? R plus PV from the second equation is more than LV from the first equation. Okay? So why do I want it in this form? And there is this error bound over here. So this directly brings me to the Bellman equation. Okay? So what is Bellman equation? Bellman equation is rho star instead of R plus the value is equal to LV star. Okay? So it is telling me that how close I am to Bellman equation is related to this error bound that I have. Okay? So now if I want to bound regret, what do? I just subtract these two equations. Okay? So rho star minus, so I subtract this equation from this equation. So compared to the optimal asymptotic average reward, what is the gap from my reward? These two essentially, so if you look at these two, you can bound these two gaps by the span of between these two. Okay? And this also you can bound by span of these two. Okay? And then this error. Okay? So basically, how far my reward is from asymptotic average reward is connected to two errors. One is the span of my current vector compared to the optimal value vector, the span gap, and the error, which is the sampling error. So this is what I call, like, the span is like the bias, right? How far my value vector is from actual value vector. And this is like the uncertainty, the sample uncertainty, right? So this I would, even if I didn't have sampling error, I would have this, because as I'm updating even in value iteration, at kth step, you have some error between the value function and the optimal value function, which depends on k. So that's the bias. And then this is the sampling error. Okay? So what we get is if I sum this over time, I get my regret is basically bounded by two parts. One is the span of my, the span gap between the value function which I'm converging to as I apply more and more L bar operators, how far I am from that, compared to the error, the sampling error. Okay? So this is, for this to be large, I should have applied a lot of L bar operators, right? I want this part, so farther I am in value iteration, the smaller the gap from my V star will be. So I want this K to be large. How many L bar I apply to be large. But if I have more K, actually I will accumulate more error also. Right? The bonuses will get accumulated over that K. So there is a trade-off between like how far you want to look back. So if I'm at current V and how far compared to which epoch I look back, if I look back a lot, I will have very small span gap between V star and my, because I have applied so many L bars. But I have also accumulated so much error because of bonuses. So that's why I don't want to look back too far, which is why this selection of this, how far I look back, how many K L operators I want to apply depends. Okay? So more details in the, I won't go through the more details about how we actually control this error. But just to summarize, like, so what we are trying to do here, we are introducing this, this assumption of frequent state, which I claim was actually satisfied by most assumptions made in the literature about average reward Q-learning. One nice thing about is that you can handle basically episodic or non-episodic or uncertain episodic, stochastic episodic, anything which, as long as you know that some frequent state, be it terminal state or start state, is visited at most H steps. Okay? And this H is just a constant bound. It should not depend on the strategy you're using and so on. So once you have that, we can show that you can use this L bar operator to get a strict contraction and get basically the same as episodic Q-learning algorithm, but with one extra step because of this terminal value that you don't have in the episodic setting. Yeah, that's my talk. Thank you. Yeah. No, the expected length. Oh, I didn't say that maybe. Yeah, the expected time is bounded by it. Yes. No. Yeah, otherwise you have to keep track of time. Yeah, expected time is bounded by H. Yes. It's actually, it looks different, but it's actually the same because one implies the other. So if you have a probability P of getting back, you have expected time bound of H over P. And if you have expected time bound of H, then you can reach 2H with half probability. You have, right? You have a probability of 1 to return to it in H. Yeah. So I'm saying the two assumptions. One is expected time to return is H, is bounded by H, or there's a lower bound on the probability P of returning. They are essentially the same within constants. Because one applies. Sometime within H rounds. Yeah. In at most H. Yeah. Any other questions? Yeah. All right. Thank you.